Look at a shimmering blue butterfly wing or a vibrant green leaf. The specific shade you see is the result of which wavelengths of light are reflected back to your eyes. The vibrant reality we experience is constructed by a constant, silent interaction between the objects around us and an invisible ocean of energy waves. This animated timeline displays the entire electromagnetic spectrum. It spans from massive radio waves to microscopic gamma rays, but right here in the middle is a tiny, highly specific sliver. Visible light waves are the only electromagnetic waves human eyes can detect. Within this sliver, the waves vary in size. At the red end of the spectrum, the waves are long and carry lower energy, measuring about 700 nanometers from peak to peak. At the violet end, the waves compress into shorter 400 nanometer intervals, carrying higher energy. To see how these microscopic measurements transform into the colors we perceive, we must follow the physical journey of a single wave from its origin in the stars to the human brain. Our journey starts at the source. Stars and the light bulbs in your ceiling are constant energy generators, pumping trillions of these invisible waves out into the environment. This beam of white light is polychromatic. When it splits open, it reveals all color wavelengths, from red to violet. But laser light is monochromatic, producing only one color. It projects a single, isolated wavelength. Because lasers pack all of their energy into one dense, unified wavelength, they can cause permanent eye damage if that light enters the pupil. In most environments, we are surrounded by chaotic, invisible fields of every color wavelength, traveling together, waiting for a physical object to hit. When that beam of polychromatic white light strikes an object, like the thick cotton fibers of a red shirt, the different wavelengths begin to interact with the fabric on a molecular level. Here, fabric molecules act as filters. As multicolored waves hit the structure, dye molecules physically absorb the shorter violet, blue, and green wavelengths. The red wavelength alone survives, bouncing off the fabric and traveling back into empty space. This mechanism determines the appearance of every object. White objects appear white because they reflect all colors. Black objects, like this liquid, absorb all colors, so no light reflects back to your eyes. Objects function as selective sponges, soaking up specific light energies and rejecting others. That surviving red wave continues until it penetrates the human pupil. It strikes the retina, a light-sensitive tissue lining the back of the eye. The retina houses two types of photoreceptors. The first are the rods, which allow us to see things in black, white, and gray, particularly in dim environments. The second are the cones. These are our biological color detectors, but they only work when the light is bright enough. This is why colors seem to vanish at night. 3 cone types detect short, medium, and long wavelengths. Short waves trigger the S receptor. Our red wave triggers the L receptor. The brain uses additive mixing, overlapping these 3 signals to create our perception of a full color spectrum. Television and computer screens operate using this same principle. They use just 3 primary colors of light, red, green, and blue, in different proportions to make the brain perceive every other color on the screen. Through this biological rendering process, humans can distinguish an estimated 10 million distinct colors by processing just 3 basic wave signals. When we return to the environment from the beginning of our journey, we can see that the colorful world around us is a psychological projection built from reflected energy. Because color is a product of biological hardware, different species experience different versions of reality. For a long time, many people thought dogs could only see in black and white. We now know that dogs have 2 kinds of color receptors. This allows them to see the world in distinct shades of yellow and purple. Every creature on Earth shares the same physical light waves, yet each biological system constructs a unique visual universe from that raw energy. Color emerges from a continuous interaction between cosmic energy, the physical structure of matter, and biological interpretation. It is a reminder of the complexity hidden in every beam of light. Stay curious.